Hello everybody, this is Mr. Walters, this is physics, and we've been talking about space, the final frontier. And we've been talking about how astronomers will analyze the light coming from distant galaxies, and they can dissect that spectrum, dissect it into individual fingerprints of the different elements. This is called a line spectrum. So let's just take a look at the periodic table. Here's iron. We talked about iron as being important for our red blood cells. So the iron ion is going to be grabbing oxygen at the right time, releasing oxygen to the tissues so that our tissues can take in that oxygen, use that oxygen to break down foodstuffs, and eventually get cellular energy to keep our cells moving in the right direction. Make no mistake though, this iron and all of these elements here are produced by the nuclear processes that are going on in stars, in suns like our own, but also in exploding supernovae. All right. We are in fact, I said it before, we are in fact, and all the matter around us, we are stardust. It sounds poetic, and it is poetic, but it's also a literal fact. Notice here we've got chnops, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's chnops, and those are the important elements of life. We also need elements such as iron, which we mentioned, but we need small amounts of zinc. We need trace amounts of some of these other elements. Calcium is an important component of our bones, all coming from stars or exploding stars. Okay. Well, notice we've got the metals over here, we've got the non-metals over here. These metals like sodium, potassium, lithium, strontium, copper, these metals, when they're energized, when they're heated up, they are going to release visible light. And that visible light can be dissected with a spectral analysis to determine the specific fingerprints or line spectra of those particular elements. In this way, we can study the components, the building blocks of suns, stars, and galaxies. And this is what I want to look at just a little bit today. All right. If we're going to study light, we need to turn out the lights. Ouch! Ouch! Get out of here. I'm back. So what I have here is a strip of a metal. Let's energize this metal and let's excite the electrons. And those electrons are going to jump out away from the nucleus, but they'll fall back down towards the nucleus, and then they're going to release light of specific wavelengths. But anyway, let's just see what we got here. See if we can get this to go. And there we go. That is magnesium. And when we energize the electrons of those atoms, we get that characteristic bright white light. Now, of course, we could analyze that bright white light. We'd have to turn on the lights to analyze that bright white light, maybe not. But anyway, we could analyze that bright white light, and we could run that bright light through a spectroscope and then look at the fingerprint of the light that's produced by that magnesium. That magnesium, this is kind of silly here talking in the dark, but that magnesium is is common in fireworks. So any bright white flashes will come from small shards of magnesium that's energized. I'm gonna see if I can turn back the lights on without bumping my shin. So we talked about metals. Metals on the middle and on the left side of the chart on the periodic table. When those metals are energized, they will, again, the electrons will become excited. The electrons will move out and jump away from their energy levels, which are closest to the nucleus, where they're most stable. And then once those excited electrons jump out, they will in fact move back down to successively lower energy levels in kind of a random fashion. And as they do that, they're going to emit a characteristic wavelength of light, which then can be used as a fingerprint for that element. So there's kind of a qualitative discussion of how those fingerprints are produced when scientists analyze light spectra with a spectroscope. We have cheap spectroscopes in here, and we can analyze light in here in a similar fashion. So we'll take a look at some of the metals and the light that they release, but now let's take a look at some of the non-metals. So what I have here is hydrogen, and we're going to energize the hydrogen. And when we energize the hydrogen, again, electrons jump out in energy levels. They'll pass back down to lower successive energy levels. They'll do this in kind of a random fashion, chaotic fashion. But when you sum up all that chaos, you will get certain wavelengths of light released, which can be used for the fingerprint analysis. So here we go. Let's turn that light off. And there we go. So that is hydrogen. Hydrogen gas is being energized there and releasing light. Now our eyes kind of take all the information and give up a kind of a sum value of the different wavelengths that are being released here. But we could run that through a spectroscope, and we would see the telltale signs, the spectral fingerprints of hydrogen. This is also really cool because we are creating a plasma in here. And essentially the hydrogen atoms are disassociating from the electrons. So the electrons and their characteristic nuclei have separated from each other. The electrons are going to travel in one direction towards what's called the anode, and then the positively charged particles will be traveling in the other direction. And this occurs in kind of a chain reaction sort of way. But anyway, this is just so cool. And again, we have a plasma. Let's take a look at helium. Now this is hot, 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 ouch, ouch, and I'm not kidding. So that's hot. Not only was visible light being produced, but also infrared light. Infrared is not visible to the naked eye, but it is commonly called heat. So infrared is just a little bit longer wavelengths than the red. Let's see if this is cooled down. Okay, there we go. Now that was hydrogen. This is helium. So again, that's pretty cool. And again, we could use that spectroscope to analyze the fingerprint. So I want you to relate this to how astronomers are studying light from distant galaxies. Well, I don't know, it's a little bit dark. Let's just look at this one. And let's turn that off. And there we go. Again, there's small amounts of gases in here. They're being energized by electricity. run electricity through these gases, and the gases are at very low pressures here. We can excite those electrons, and then those electrons will, again, I know I'm repeating it, but the concept, this is directly related to the quantum concept of matter, quantum mechanics, and this is fundamental in physics, and it's fundamental in chemistry. It's an enduring theory that has withstood the tests, all the tests of time over the last 70, 80 years. It really is reality on a micro scale. Well, here are several ionic salts. On the left here, we have sodium chloride. So this is table salt. And I've got some sodium chloride in here. And here we have potassium chloride. I also, over to the other side, I've got strontium chloride. So strontium chloride salt. So this is an ionic salt. High melting point, crystalline solid. There's copper chloride over here, out of your field of view. But what I want to do is energize those. And we're going to energize those metal salts with a flame. And we're going to look for a color, a specific color to be released. What's going on in the universe is the metals are being energized by the nuclear fusion processes that are going on in the sun. All right, here we are. Let there be light. You may have discussed this in other classes. I certainly have in my advanced chemistry, but it doesn't hurt to... So take a look there. Look, the blue is the alcohol. Look for flickering. Look for flickering orange. Now this really begins to become enhanced as most of the alcohol burns off. So that is potassium chloride. So let's let that get down to where the salt is and look for flickers of light besides the blue. Now that's pretty good. So there's potassium. Boy, that's really good. Is the strontium. Again, blue is the methanol. So that's the alcohol. Now there, boy, that looks good. Shoot, I'm getting a vivid red color. I don't know if the video's showing it as well. Boy, that's as good as it gets there. So that's strontium chloride, SrCl2. And again, I like it when it gets down to where there's very little alcohol and you got a lot of salt. Let's take a look here. So I overdid it on purpose here for the cool effect. This is copper chloride, so the heavy metal is the copper. And again, I'm getting just a vivid green. And the video, I don't know if that's doing it justice or not. Energized metal cations here. So in the furnace of the suns of the galaxies, you're energizing metal atoms, and they'll be releasing characteristic photons of energy. Little photons, little particles. Of course, those photons, which act as particles, are both, they have a characteristic wavelength, and they also are a little packet of energy. They're both. They have a wave and they also have a particle role. Light, wave, particle, duality. I don't know if I said that right. Particle, wave, duality of light. The electromagnetic spectrum consists of waves, and we've talked a lot about waves, wavelengths with frequencies. But there's also a particle component of light and all the different regions of the electromagnetic spectrum. So it actually behaves as both, and evidence supports both ideas, that it's both particle, packets, but also long drawn out waves. It is, yes, it is a paradox, but there's experimental evidence that supports both types of behavior, which is amazing. Totally amazing. And there we go. So here is the grand finale. Notice all the different energized salts. Strontium is red, copper green, sodium's orangish, potassium is violet, left, sodium, next going from left to right, potassium salt, then strontium with the red flame, and then copper with the green. All right, still in the dark. Yes, as can happen on occasion. Well, I'd be remiss if I didn't mention how any of this relates to pyrotechnics, and there's an art and science into making fireworks. So you're adding the proper amounts of magnesium, get that bright white flickering light, but then you're also adding varying amounts of these metal salts. And again, I don't propose to be even close to an expert on this, but that's the general idea as far as I understand it. Anyway, so right now, let's take a look. We're going to do one more flame test. This is flame test on steroids. All right, I want you looking for the color. Look for the color. Is it a chloride salt? Is it a strontium salt, potassium salt, whatever? Let's turn off this light here, and let's see what we got. No money back guarantees here. That's not bad. All right. I don't know. I'm not great with colors. You decide what salt was in there.